I'm going to show you why infinity is not an option when it comes to the Collatz conjecture. And by the way, this is my photograph. I think it's spectacular. And the reason I chose a cobweb is because if one sequence is infinite, then a huge set of other sequences must be infinite. About 1/4 of the natural numbers will be in an infinite set if one sequence is infinite. So, bearing that in mind, let's continue. So, I'm looking at a subset of numbers of the form 8n plus 5, which is sufficient to solve the 3x plus 1 problem, and I'll show you why. So, numbers of the form in 8n plus 5, such that n is odd, belong to a set that begins 5, 13, 21, 29, 37, and so on. So these numbers are 8 apart, beginning with 5. And it's a sequence or a series of numbers that I've spoken about many times before. I just haven't used the 8n plus 5 definition. Someone pointed out that the way I was expressing the congruence was actually not correct. It works in the functions I use as the third option, but it's better said another way. And this is fine, 8n plus 5. It can be expressed as a congruence as well. So what we're looking at here is subtraction by 1 and division by 4 yields the consecutive odd numbers using the operation that I apply to these numbers of this form. So it's very, very simple. You subtract 1 and you divide by 4. So 5, input 5, output 1, input 13, output 3, input 21, output 5, input 29, output 7. So you see right away that we, as an output, we're getting all of the consecutive odd numbers without exception. So, how does this operation, n minus 1 divided by 4, have relevance to 3x plus 1 sequences? Well, first let me give you a graphical representation, and I'll just get the pointer, and you see this column represents n minus 1 divided by 4, as we just mentioned, and we see that these same numbers are here, 8 apart. And then using the operation, which is exactly the same as the formula at the top, we get the consecutive odd integers. So let's just bring it home graphically and showing which numbers are not included. We have these two other columns which represent different congruence classes. And when we look at this, we will see that all the numbers not divisible by 3 have two outputs that are the same. So, for example, 9 and 7 and 29 and 7. So that's what I've shown here, 9 and 7, 29 and 7. And then I've shown 7 and 11 and 45 and 11. So you'll notice that there is one number represented in the first two columns and one that's represented in the third column. There's always one in the third column. There's always one of this type, m minus 1 times 4 divided by 4. Excuse me. So what we get from this is that there's a convergence, a type of convergence occurring on every odd number that you can output. There must be. So you see since every integer is represented in the third column of the output, and it's represented again once in the first two columns, then every number is output using these operations twice. They merge. 2 7s, it's really 1 7, so we're merging 9 and 29. 2 11s, so we're really merging 7 and 45 on 11. Hope that's clear enough. Now, here we're going to switch to sequences, and the first number of a sequence is arbitrary in my opinion. You know, whatever you pick has a preceding number. It doesn't matter what it is. But for our purposes, we're going to use the conventional approach of considering S to be the first number of a sequence, whatever S is. When you multiply 4S plus 1, which is the inverse, shall we say, of n minus 1 divided by 4, so when we multiply 4s plus 1 by 3m plus 1, which is the Collatz function, or the first part of it, we do it like this, so s times 4, and then plus 1, then multiplied by 3, and then plus 1. The odd s of the first sequence is replaced with 4s plus 1, obviously, and 3 or more even steps follow from division by 2. So that's the Collatz function. But the first bit, the s times 4, or 4s, is just not represented in the conventional function. And I'll explain why that is. That's really the whole point. The apparent second sequence is a continuation of the first, or the first a continuation of the second, if you prefer. For example, if s equals 31, then let's just take this apart. So 31 times 4 is 124. And the factors of 124 are 2 times 2 times 31. When we multiply by 4, we get 2 factors of 2. Then we add 1 to that to make it an odd number, because, well, I only consider odd numbers normally. Here I'm illustrating the relationship between the even and the odd numbers to explain why in the even-odd sequences you do not see this very salient fact that the sequence is actually continuing by multiplying by 4 and adding 1. So once we have that, we have 125, 124 plus 1, we have 125. Now we multiply that by 3 and add 1, we get 376, and then we divide this as many times as possible, which is 3 in this case, times 47. That's the factorization of 376, or the factoring, excuse me. So this translates into two sequences. What appears superficially to be two sequences, it's not. 31 becomes 94, becomes 47. And 125 becomes 376, 188, 94, it merges, and then 47. Okay, I think this is the thing that mathematicians really are missing, this 4n plus 1 repetition of the same sequence. It's not even, it's better just to think of it as a continuation of the same sequence, really. So that's why I said you might want to think about the continuation of sequences as either a branch or a merge in the context of 4x plus 1 and m minus 1 divided by 4 respectively. So, you know, you're either going up the sequence or down the sequence, where down the sequence means going to 1. And by the way, the subject of a discussion is infinity is not an option, that means that it's not possible for a sequence not to end in 1. So I just want to clarify that, if you think about this logically, you can extend a sequence back forever in the direction of infinity, but it converges on 1. The proposition that has to be disproved with respect to the conjecture is that the sequence never goes to 1 forever, for infinity. So it might seem a bit abstract, what I've just said about continuation of sequences, until you realize that, for example, if S equals 27, S times 4 plus 1 equals 109. However, the conventional wisdom of mathematicians regards 27 as a sequence that has no continuation. And that's because it's a multiple of 3. Well, here's the news. 109 is clearly the continuation. And if you check out the sequences for yourself, you will see there's a merge. I think it's on 41 and actually 82. When you're satisfied that this is true, you can consider the continuation from 109 to 437, again, times 4 plus 1. So what is it about 27? And I always come back to 27 because it's such a long sequence, relative to other small numbers. So it just happens to be that 27 minus 1 is not divisible by 4. That's all. Like 3 out of 4 numbers are not divisible by 4. So there is a branch that leads to 27 with the operation m minus 1 divided by 4 that is ignored by mathematicians. And I maintain that that's illogical, incorrect, and self-defeating. The fact that 27 happens to be a long sequence is quite irrelevant. It's the smallest sequence in this series that I've just described. So I think of this process as prepending of even numbers and one odd number at the beginning. In all other respects, the order isomorphic set that is each sequence is the same. They will be the same for any nth term of the sequence. Now, for example, consider 69 multiplied by 4 plus 1, 277, multiply that by 4 plus 1, 1109, and so on, 4437, 17749. Now, you will see that these sequences are really truly the same. There's just a prepended even numbers, and in each case the first odd number is superseded by a multiple of 4 plus 1, and then you don't see the original number, but you see the merge, and it's totally predictable. You see these prepended even numbers. I think it's pretty hard to believe that mathematicians don't see this, but the evidence I've seen is that at least these really big number computations of Collatz sequences are just repeating these 4x plus 1 sequences over and over again. They only needed to do it once and strike it off their list, every multiple of 4 plus 1. I don't get it. This is the continuation of one sequence and not 5. Any sequence can be infinitely extended with 4n plus 1 up the number line, effectively. The sole thing that is changing with each iteration of a sequence is this little knot of s times 4 plus 1 times 3 plus 1. So it's like a little knot where the s times 4 is hidden in some way, apparently, to some people. So there can be no other outcome. Every power of 2 can be represented as 4k plus 1 times 3 plus 1. And well, this is very interesting because we can see that each iteration of a sequence extends a partial power of 2 to the odd number following the first s. And so this is actually easier to see when you are applying the m-1 divided by 4, shall we say the forward operation, the one that goes to 1. And when you do this, you see with each case that it's proceeding to the odd number following the first odd number of the hypothetical sequence. So this is a very nice finding, and actually inevitably takes you to 1. So it turns out that the most naive thought about the provability of a conjecture, which newbies have concerning powers of 2, has a lot of relevance after all. This really, again, so any 4k plus 1, and so I'm changed s to k, any 4k plus 1 multiplied by 3s, multiplied by 3 plus 1 is going to be a potential power of 2. Maybe better to say every power of 2 can be represented as that formula. Now, so this leads to, actually it doesn't lead directly to this, but we may state the nth term of every sequence fairly easily. I have a couple of previous videos about this, but so this is an nth term formula, and it's saying that there's an answer for the nth term for the geometric progression of 4n plus 1, whereby if 4 exponent n, which is the term minus 1 divided by 3, gives you that, the value of that. So it's trivial to adapt this to any sequence, and I did that by doing add 4 to the power of n, the term, times the sequence number. And that gives you the number of steps, additional steps in the sequence. And that does not require a high IQ because it's essentially each term has one more sequence in an odd sequence. And it's just nice to be able to do this and underline the obvious here. So imagine for a moment, and this is like a thought experiment, imagine for a moment that there was a number s that began an infinitely divergent sequence. And just imagine that. If it did, then every nth term greater than s would be infinite also, because they're just continuations of the infinite sequence. However, that's impossible because the operation m-1 divided by 4 applied to any term greater than s must result eventually in an odd m-1 less than or equal to s. So that is not divisible by 4. So therefore a consecutive odd counting number. So it just falls into line with all the other counting numbers. So by the exclusion principle, which is like the pigeonhole principle, since the set of odd integers has no missing elements in this case, there cannot be an infinitely divergent sequence with respect to 1. You might imagine this like a can of sardines all pressed together. There's no way that one of the sardines could wiggle out of this pattern. There's a pattern here. So if that doesn't quite do it for you, consider the two additional operations that act on n. And if you think back to the table, there's a first and second column, and I'm just going to touch on those very, very briefly. These two operations exactly match what happens using the conventional Collatz function. They just are shortcuts. So n plus 1 multiplied by 1.5 minus 1 is a growth operation, produces a whole number, of course. n minus 1 multiplied by 0.75 plus 1 again produces a whole number, and it's a reducing operation. It reduces the size of the number. Now, the point I want to make is that, and if you go back to, if you think about the table at the beginning, where you had the two columns on the left, and one of those had to be an input for the output number, similarly, one of these two operations has to be an input for the output number, one of two. And so there's this convergence going on. So I'm showing schematically that if there were a sequence going to infinity, what would happen to the convergence, which is just arithmetically determined by these two operations? It's impossible to see how this infinite sequence could exist unless it was propagated to all the other sequences. All the other sequences would necessarily have to be infinite if they have an intersection with this sequence. So it's really, that's the logical absurdity of it. We're at the end, and the takeaway is realizing that for there to be an infinitely divergent sequence with respect to 1, it would be an infinite set of numbers that are disjoint from the infinite set of convergent numbers. And this would mean there could be not a single intersection between the numbers. There could not be one number that is the same in both sets. Now, given the function I have described, the operations of the function I have described, that is not possible. Thank you.